All right, let's talk about the giant AI models we hear about every single day. We're going to go under the hood because it turns out a lot of them are incredibly bloated and inefficient. But the cool part is we're now figuring out exactly how to fix them.
Okay, so here's the game plan. First, we need to understand this core problem, this disconnect between how models are trained and how they're actually used. Then we'll go on a hunt to find where all the waste is hiding. After that, we'll walk through how to trim it, talk about why a faster model is often better than a smarter one, and finally, look at the really exciting future this all opens up.
So the whole issue really starts with this fundamental conflict. The way we build these massive AI models is optimized for learning, for potential. But the way we use them in the real world is all about performance. You know, it's like training a world-class powerlifter who can do 1 million different exercises, when all you really need them to do is run a 100-meter dash.
And this quote it nails the central idea perfectly. During training, we build these models with enormous capacity, so they can learn anything and everything. But then, when we deploy them for a specific job, they end up using just a tiny, tiny fraction of that power. And that mismatch, that's the root cause of all the inefficiency we're talking about.
This slide really breaks down the two completely different worlds these models live in. On one hand, you've got the training phase. It's all about stability and making sure the model has this huge, fertile ground for new skills to emerge. But on the other hand, you have the real world, what we call inference. And here, the rules are totally different. All that matters is speed, cost, and how much energy you're burning. The goals are basically pulling in opposite directions. So if these models are just ignoring most of their own brain power, where exactly is all this waste hiding? Well, let's pop the hood and find out. Turns out the bloat is hiding in plain sight, right inside the model's architecture. And here's our first big clue. In these models, something like 70% of their total size, all their complexity, is packed into one component, the feed-forward network layers, or FFNs. You can kind of think of these as the parts of the model that do the deep thinking after it's read the input. This is where a ton of the computational heavy lifting happens. Now get this. This is the real shocker. Inside that massive 70% chunk, researchers have found that a staggering 30 to 60% of the neurons are basically asleep. They almost never fire when the model is actually being used. They're just sitting there, taking up space and electricity for pretty much no reason. And what's really crucial to understand is that this isn't just one leaky pipe. The whole system has dead weight. You have these things called attention heads, which help the model focus on important words, that literally just end up tracking commas. You've got that huge portion of sleepy neurons we just mentioned. And you even have entire layers of the network that basically just pass information along without doing much of anything. Okay, enough about the problem. How do we actually fix this? Well, researchers have been developing a playbook for intelligently finding and removing all this waste. The process is called pruning, and it's basically like trimming the fat, neuron by neuron. For those lazy attention heads, the fix is actually pretty simple. First, you just measure how much each one is actually doing. Then, you chop off the bottom 20 to 40%, the ones that are just dead weight. After a super quick retraining session, the model bounces right back, and you get a nice speed boost with almost no hit to quality.
And we can do pretty much the same thing with those huge FFN layers. You watch to see which neurons are firing and which aren't, and then you just prune the quietest 30 to 50%. You can use a really efficient technique like LoRa to quickly reteach the model anything it might have lost. And the result? A much smaller, much faster model.
But get this, it doesn't even stop there. You don't just have to trim individual neurons. It turns out you can be way more aggressive. Researchers are finding you can rip out 10 to 20% of the model's entire layers, and it barely affects the final performance. It's wild. Now, you might be thinking, wait a second, aren't we losing accuracy here? Why would we ever want to do that? And that's a great question. The answer forces us to completely rethink how we measure what makes an AI model good in the first place. See, in the academic world, it's all about these abstract benchmark scores. But out here, in the real world, where people are actually trying to build products, those numbers don't matter nearly as much as these do. How fast is it? How much does it cost every time someone uses it? And how much power does it suck up? That's what defines real value. So that brings us to the key takeaway, a model that's 0.5% worse on some test, but is 40% faster and cheaper to run. In the real world, that's not just a small win.
That is the undisputed champion every single time. That trade-off is a massive game changer. So where does all this lead? Well, this is about way more than just making models smaller. This whole approach is cracking open a really fascinating, really powerful new frontier for the future of AI.
And this right here is the big mind shift we all need to make. We have to stop thinking of this as compression, like zipping a file. That's not what's happening. This is model specialization. We're taking a general one-size-fits-all model and we're carving it into a lean, mean, specialized tool that's perfect for the job it needs to do. And once you start thinking that way, it unlocks all these incredible new research paths. I mean, imagine models that are custom pruned for the specific tasks they'll be doing. Or even crazier, adaptive models that can turn entire layers on or off depending on how hard your question is. We're also seeing new ways to measure performance, like accuracy per dollar. And of course, super important work on how all this trimming affects model safety. And that kind of leaves us with this final big question to think about. If we can really move away from these giant, inefficient, one-size-fits-all models and toward a world of perfectly specialized, hyper-efficient AI tools, what does that future really look like? It probably looks like a future where AI is not just more powerful, but way more accessible, affordable, and sustainable for all of us.